Welcome back, everybody. In this video, we're going to finish up section 3.2. We have one more example to do of the empirical rule, and then we're going to go on to the something called the coefficient of variation. So the story for this one is that a data set has a mean of 12.5 and a standard deviation of 3.4. And then based on this, we want to find the percentage of data that is less than 5.7 or more than 22.7. So as before, where we'll want to start is with a little sketch. So let's draw our distribution and then try to label it. So the mean, as you recall, will go at the middle. The mean was 12.5. And then our lower end was 5.7. And then our upper end was 22.7. So one thing different about this one versus our earlier examples is that instead of looking for the data in one interval, kind of including the mean, we're looking for the extremes this time, what's below 5.7 or above 22.7. So we just need to know how many standard deviations that is so that we can apply the empirical rule. So let me take 22.7 first. So we'll have 22.7, which is our upper end, minus the mean of 12.5. And we're going to divide that by our standard deviation of 3.4. So let's calculate. That's 3. Okay, so I'm betting the other end is the same, but let's check. So we'll have 12.5 minus 5.7, and that's divided by 3.4. That's 2, actually. Okay, so that's interesting. So one side is 2 standard deviations, the other one is 3. So let's think about that for a minute. Here's our picture of our bell curve. So we know that 100% of data is in the whole distribution, okay? We also know that the mean is at the center of the distribution. So that means that we would expect 50% to be below the mean and 50% to be above the mean. So then if the interval from 12.5 down to 5.7, that's 2 standard deviations, we would expect half of 95%, or 47.5% of the data to lie in this interval. Okay, in between the mean and the mean minus 2 standard deviations. That's off of our empirical rule chart. Okay, 47%, 47.5% of the data lies from the mean to a point 2 standard deviations below the mean, because 95% of data is within 2. Half of 95, 47.5. Okay, all right. So then, if all of the data is with 100% of the data is somewhere in this picture, half of it is below the mean, and I know 47% is the part drawn here, then what's left is the remaining 2.5%. So in the left tail, we'll have 2.5% of the data. Okay, so now on the right, we have the mean plus 3 standard deviations. Okay, so we know that the whole right half of the picture is 50% of the data, and then we're going to be 3 standard deviations above the mean. We know that 99.7% of the data is within 3 standard deviations. So get out your calculator. 99.7 divided by 2 is 49.85. 49.85% of the data is on the right side of the mean. So the rest of it, that remaining 0.15% of the data, has to be in that right tail. Okay, so the total then between those two is going to be 2.65. That's 2.5% plus the 0.15% is 2.65%. This, like the last example in the last video, involves a situation where the interval is not symmetric around the mean. All right, so that's probably enough of that for now. Let me know if you have questions about that, because it takes a little while to get used to it. All right, so moving on, less calculation, a little more conceptual for a little bit. So the next thing we want to look at is something called Chebyshev's theorem. This is named after a Russian mathematician and a person who studied probability a long time ago. And the statement of the theorem goes like this: the proportion or fraction of any set of data lying within k standard deviations of the mean is always at least, that is, it could be more, it's always at least 1 minus 1 over k squared, where k is any positive number greater than 1, like 2 or 3 or 4. Okay, for k equal to 2 and k equal to 3, we get the following statements. At least 3/4 or 75% of all values lie within 2 standard deviations of the mean. At least 8/9, which is the same as around 89% of the data, lies within 3 standard deviations of the mean. So 2 things to go with that. One is, where did these 3/4 and 8/9 come from? Let's deal with that part first. So that comes from this formula right here at the top. The 1 minus 1 over k squared, k is the number of standard deviations, okay? So 1 minus 1 over 2 squared, okay, that's 1 minus 1 over 4, and 1 minus 1/4 is 3/4. For the 3, it's 1 minus 1 over 3 squared. That's 1 minus 1/9, and that is 8/9. That's where they're getting the 3/4, which is 75%, and the 8/9, which is 89%. The other thing then that we have to talk about is, why is it 75% now when, like 5 minutes ago, I just said that it was 95% of the data within 2 standard deviations of the mean, and 99.7% within 3. And now that I turned the page, it's 89%. So what's with that? So the thing is that Chebyshev's theorem applies to any distribution, whether it's bell-shaped or not. The earlier examples that we did with the body temperature and this one, we were basically given, I didn't come right out and say it, but we were basically given that the data had a normal or bell-shaped distribution. The thing is, if you know the shape of the distribution, you know to some extent how the data is spread out. So if you don't, you can apply Chebyshev's theorem. It is more general in a sense than the empirical rule is, because it applies to any distribution. So let's think about that and just test it to see if it makes sense. For the last example we did, if the distribution of data is normal, let's say, we know according to the empirical rule that at least that 95% of the data is within 2 standard deviations of the mean. If it's 95, then would that be this? Is it true that at least 75% of the data is within 2 standard deviations of the mean? Yes, it would be true. If that's unclear, here's another example that just illustrates the relation between the numbers. Suppose that I told you that you needed to end up with a 75% on the final in order to pass, at least to 75. Let's say somehow you got a 95% on the final. Would you still pass? Yes, because your 95 is definitely at least 75, okay? So the thing is that if we know the distribution is normal or bell-shaped, we can say that it follows this 68, 95, 99.7% pattern. If we don't, if it's just any old set of data, and we don't know that it's normally distributed, then we can at least say the criteria that Chebyshev's theorem gives us. Okay, so we're gonna have an example that illustrates that. Okay, so let's see that. All right, so cans of regular Coke have a volume in this sample that has a mean of 12.19 ounces, and a standard deviation of 0.11 ounces. So 12.19 minus 2.11, that's 11.97. And then let me add the 2 standard deviations to it. Okay, that's 12.41. Okay, so according to Chebyshev's theorem, that was 2 standard deviations. So according to Chebyshev's theorem, at least 75% of cans of Coke weigh between 11.97 and 12.41 ounces. Okay, I should say their volumes, not their weight, but that's okay. If we know that they're normally distributed, then it's going to be around 95% of the data. So if we, the point is here, that if we just have this set of data and we don't know if it's normally distributed, we can use Chebyshev's theorem to say something about the distribution of the values. If we do know that it is normally distributed, we're able to say more about it. Okay. All right, so the next thing that we're doing is looking at, we're almost done with this section. We have basically one more topic, and that's the idea of the coefficient of variation. Okay, so we'd mentioned back in part 1 of this section that if you're comparing variation in 2 different sets of data, the standard deviations should be compared only if the 2 sets of data have the same scale and the units and approximately the same mean. If the means are significantly different, or if the samples use different scales or different measurements units, we can use the coefficient of variation defined here. So here's formula and then some examples. So the coefficient of variation, abbreviated CV, for a set of non-negative sample or population data expressed as a percent, describes the standard deviation relative to the mean in the following way. Basically, these 2 formulas are the same. It's just that one of them is for population and one's for sample. We're going to take the standard deviation and divide by the mean. So it's S over X bar for a sample, or sigma over mu for the population. So the standard deviation over the mean, regardless of whether it's sample or population, and then multiply by 100% to turn it into a percentage to make the coefficient of variation. All right, so that is how it's calculated. There's a round off rule for it. It's a percent, okay? So it's not in feet or inches or anything. So you can always round it to 1 decimal place. So for example, 18.3%. All right, so the purpose of the coefficient of variation, why use it? If you are dealing with quantities that have drastically different means, or drastically different standard deviations, then you're going to get better results comparing their coefficients of variation. For example, let's say that you have weights of a bunch of adult people, let's say the people in this class, okay? We could measure everyone's weight and we could calculate the mean and standard deviation. Okay, so the standard deviation will probably come out in the range of 5 pounds, 10 pounds, something like that, okay? So we could estimate that, 5 to 10 pounds. But let's say that we had then a list of like 25 babies that were 2 days old, okay? Babies are going to not have a variability in their weights that is going to be measured in like 10 to 20 pounds, right? That's more than the babies are going to weigh in the first place. So in order to compare the variability, we wouldn't say, okay, well, these babies have a standard deviation of like 2 ounces in their variability of their weights, whereas this group of adults has a variability that's like 23 pounds. And then based on that, conclude that the adults are more variable, right? Because the 2 means are really far away, okay? Another example would be if we're comparing 2 different qualities altogether. So let's say that we're comparing people's heights against people's weights. We can't really say, okay, well, if the standard deviation is in inches and this standard deviation is in pounds, how can you compare the 2 and say, okay, well, one's larger than the other? So what we have to do is turn it into a percentage, okay? And that's basically how that's going to have to go. All right, so I want to see some examples. For the first one, we're going to go back to this two banks problem that we had had before. We saw that their measures of center were all the same, and then we calculated their standard deviations. So we're going to calculate the coefficient of variation for both banks and use that to determine which is more variable. So let me put all of this into StatCrunch, and then we'll get the standard deviations, and then we'll go from there with the coefficients of variation. All right, so I've got the data put into StatCrunch again, and so I wanted to get the mean and standard deviation so that we're able to calculate that coefficient of variation. So we have columns for JVB and BOP for the two banks. We're going to go to Stat and then Summary Stat. So our data is in columns, okay? I want the two columns, so I'm going to select the first column. I'll hold down Shift and select the second column. And then this time we only want the mean and standard deviation. So let me get rid of some of this. Let's just take the mean and standard deviation. Are they going to give me the variance? Standard deviation right in front of my face. All right, three things, fine. Okay. Okay, so then we've got a standard deviation for Jefferson Valley Bank of 0.4766. And then the mean, this example actually isn't that exciting because the two means are the same. But that's okay. We'll go with the calculation anyways. So Bank of Providence had a standard deviation of 1.821. So let's go ahead and calculate those two coefficients of variation. All right, so going through the calculations here, we divided the standard deviation by the mean in each case and then multiplied by 100% for both. So it turns out that Jefferson Valley Bank had a coefficient of variation of 6.7% and Bank of Providence 25.5%. Like I said, this example is not all that satisfying because in this case, the two means were exactly the same. So we could just as well have compared the standard deviation. We'll have another example here in a second that will be more interesting, but I did want to make sure to emphasize that in calculating the coefficient of variation, it's the standard deviation on top and the mean on the bottom. Very frequently people get that backwards and divide the mean by the standard deviation when really it should be the other way around. Okay, so let's have another example that is more fun. All right, so here's another set of data we can use, and maybe this will be more interesting. So the data set here I just found by looking through the StatCrunch's sample data. So it says that this is the median price, sales price of a home versus the median rent in 12 cities. And so the data is shown as here. So let's go ahead and calculate the summary stats data is shown in columns. And our two columns are going to be the sales price and the rent, of course. And then let's take just the mean and standard deviation. We'll pick up the variance as well. Okay, so the thing is that we can't really compare the two standard deviations directly. One has a standard deviation of 140,000, but the other one's only 467. It's not really fair to try to compare those two because we have to compare them in the context of the mean. We can't just take the higher selling price or the higher variance or standard deviation among the sales price. We have to compare it actually to the mean. So let's go ahead and make that calculation. All right, so going through the calculations there, it turns out that the selling price or sales price in these cities had a variability, a coefficient of variation of 42.8%, and the rent was 25.3%. So that says across these cities, it looks like selling price was much more variable, or said the other way around, that the rent was more sane, more constant across those cities. So that's that. I'll leave it to you to think about why that might be true. And then in the meantime, we're going to go on to another example. We have two more examples and then we're done. Okay, so the first one is a set of climate data. This is taken off of Wikipedia, so you can judge the quality of the source there. I'll leave that to you. But this is temperature data for Palm Desert. And we've got the high and low temperatures, the average high and average low monthly over the course of a year. And to save a little time, I've calculated already the standard deviation and the mean. And so we're just going to calculate the coefficient of variation and compare the two. So you want to remember that it's standard deviation divided by mean. So that's in the first case, 13.53 divided by 89.4. So that is about 15.1%. Okay, and then for the lows, 13.39 divided by 62, or about 21.6%. Okay, and so again, how to interpret that? The two means were different. The two standard deviations actually were relatively close to each other, which is interesting, but between the two, it looks like the low temperatures are more variable, which is interesting. The high temperatures are much more the same. So how hot it gets is more consistent over the course of the year. How low it gets varies more over the course of the year, at least in this one city. All right, last example. This is our Presidents of the United States data set. Here it keeps track of the name, age at inauguration, days, I believe, in office, years in office, height, and height of their opponent, both in centimeters. So I've taken just the data for their age and their heights, and we've got the means and standard deviations for both. So I'll give you a second, or you should take a minute to pause the video and calculate the two coefficients of variation. Before you do that, you want to use kind of your common sense to try to predict which one you think is going to be higher, and we're going to see how that comes out. All right, so going through the calculations, their ages worked out to be 12%, the coefficient of variation, their heights 4.1%. Here we did need to calculate the coefficients of variations because you can't just compare years against centimeters and say which is bigger based on that, of course, right? So we had to change both to a percent. It looks like their ages are more variable than their heights. And so you can think about why that might be so too. I think that there's younger presidents and older presidents, especially over the life of our country. But I think that people are less likely to tolerate variations in people's heights. But that's just my opinion. So anyways, that takes us to the end of section 3.2 on measures of variation. Let me know if you have any questions, and have a great day.